Alright, hello, welcome to this week of our Math 2413 weekly reviews. This week we're going to be going over chain rule, implicit differentiation, and a little bit of inverse trig. So first thing we're going to go ahead and work on is our chain rule. So now let's go ahead and define what our chain rule actually is. So our chain rule states that if we have a function g, if our function g is differentiable at x, and if another function f is differentiable at g of x, then the composite function f of x is going to be equal to the smaller f of g of x and f prime can be solved by saying that f prime of x is equal to the derivative initial f of g of x times the derivative of g of x. Or if we wanted to put this in Leibniz notation, we can also say that dy over dx equals to dy over du times du over dx when y equals f of u and u equals g of x. So essentially what this is saying is that if we're wanting to derive a composite function, and we're going to take the derivative of the outside and leave the inside the same, and multiply that times the derivative of the inside. So essentially what we're doing is we're actually just kind of working outside in. So now let's go ahead and do a couple of examples. All right. So for our first example, we have we are going to say that y equals the fifth root of x squared plus 2x plus 4. And we're wanting to know what is y prime. So the first thing we can do is try to find our inner and our outer function. So let's go ahead and rewrite this function as saying that we have y equals x squared plus 2x plus 4 to the 1/5. What we can do is we can actually say that we can treat this whole big exponent right here and let that be our outer function. Let's go and call this f of x. Now we have this function inside of that, this x squared plus 2x plus 4. That's going to be our inner function, which we can call g of x. So if we call back to our rule earlier, it says that f prime of x is equal to f prime of g of x times g prime of x. So now let's go ahead and plug this in. So if we derive this 1/5, this whole thing to the 1/5 power, we can go ahead and bring down that 1/5. And then we can go ahead and then that new power is going to be down to a -4/5. And then we can just go ahead and leave the inside the same. Now we need to go ahead and derive our inner function. So if our inner function is going to be x squared plus 2x plus 4, the derivative of x squared is 2x, and the derivative of 2x is 2, and the derivative of 4 is 0. So we're just going to multiply 2x plus 2 times the derivative of f prime of g. So therefore, final derivative is going to be 1/5 times x squared plus 2x plus 4 times to the -4/5 times 2x plus 2. So now let's try another one. This time we're wanting to find This time we're going to have y equals tangent squared of x. And once again, we're wanting to find our y prime. So now let's think about what we have. We have tangent squared of x, and what we can actually do is whenever we have a trig function like this, at pretty much any case except for a -1, what we can do is we can actually pull this number out and rewrite it as saying tangent of x all squared. Now, -1, you have to be careful because that's when you start getting into inverse trig, and you have to be a little more careful with that. But for most numbers, you can just go ahead and pull it out and create a new exponent. Now we have this, we can actually once again say that we have a composite function. We have this whole thing being squared, which is going to be our outer function, which is going to be our f of x. And then we can have tangent of x just be our inner function, which is just going to be our g of x. All right, now let's go ahead and once again solve this back end. So we have our outer function, which is going to be things squared. So we can go ahead and pull that 2 out in front. And then our exponent would be 2 minus 1, so just 1, so we don't even have to write it. And then our inner function stays the same for right here. We can just leave it as tangent of x. Now our derivative of tangent of x is going to be secant squared of x. So we can multiply that times what we already had, and therefore our final answer is going to be y prime equals to 2 tangent of x times secant squared of x. And that brings us up to like a cool little just quick property that we can talk about. We can actually find a more specific chain rule when it comes to power rule. If we have power and chain rule, we can actually just go ahead and say that if we have some function u to the n where n is any number, or n is any real number, and u equals g of x, then we can say that the derivative of u to the n is equal to n times u to the n minus 1 times du over dx. So that's just essentially just a quick little way just to kind of, in a way, bypass chain rule, or just another way of saying it in a more specific light when it comes to power rule. So now let's do this one more time. Let's try an example. Once again, using power plus chain rule. So this time we're going to have our function. This time we're going to derive the function one over 3x squared plus 4x plus 2 cubed. So now let's go ahead and think about how we can relate this to power and chain rule. First thing we can do is we can relate this to power rule by rewriting our function as, we can say that we have 3x squared plus 4x plus 2 all to the negative 3. Now we have something that is in terms of power rule, and we also have something in terms of chain rule. So now let's go ahead and just kind of go and plug everything back. So we know that our u, so we can say that our u is equal to 3x squared plus 4x plus 2, and then our n equals negative 3. So now we can just go ahead and plug that out. Plug this in to where we have d over dx of u to the n equals n to the u to the n minus 1 times du over dx. All right, so we have our n, which is negative 3, which we can just go ahead and pull out in front. We have our u to the n minus 1, so we can go ahead and keep that 3x squared plus 4x plus 2, negative 3 minus 1 is going to be negative 4. And then our du over dx is just going to once again be the derivative of our u. So the derivative of 3x squared is going to just be 6x. And the derivative of 4x is just going to be 4. And then derivative of 2 is 0. So we can go ahead and just quickly rewrite this as saying that we have negative 3 times 6x plus 4 all over 3x squared plus 4x plus 2 to the 4th. And we can even go one step more and distribute out that 3 to where we have negative 18x minus 12 all over 3x squared plus 4x plus 2 all to the 4th. All right, so now let's try another one that's not solely reliant on just power and chain rule. This time, we're going to have you're going to be taking the derivative of 2 sine of 3x plus tangent of x. So now let's go ahead and look at this and see what our inner and outer functions are going to be. Let's go ahead. We can go ahead and see that we have this sine that's around a big thing, so we can let sine be our outer function. And then we have this inner function, 3x plus tangent of x, that is, and all of that's going to be inside of that sine function, so therefore that's going to be our inner g of x. Now let's go ahead and start plugging this in and trying to figure, and plugging this back in. So if we take the derivative of sine of x, that's going to be cosine. We take the derivative of 2 sine of x, that's going to leave us with 2 cosine of x. But since this is chain rule, it's just going to be 2, instead of x, we're going to have that full function that we have inside. So it's going to be 2 cosine of 3x plus tangent of x. Now we can take our derivative of the inside function, which is going to be 3x plus tangent of x, which is going to leave us the derivative of 3x is 3, and the derivative of tangent is secant squared. Therefore, our final answer is going to be 2 cosine of 3x plus tangent of x times 3 plus secant squared of x. Now let's try a couple more. This time let's go ahead and try to see what happens if we try using exponential functions. So let's go ahead and try, this time we're going to take the derivative of e to the 2x squared plus 3. This one's a little interesting. That one's a little, this is a little different, but we can still see that we can go ahead and have an inner function, and then we have an outer function. So where we can think about this to where our inner function is going to be 2x squared plus 3. And we can think of this as our outer function as being equal to just e to the x. So now let's go ahead and move forward. So if we take the derivative of our outer function, which is e to the x, or in this case, e to a function, then we can just go ahead and just need to know that we just leave it as is. So we can just leave it as is and say that we have e to the 2x squared plus 3. But since this time we're using chain rule, we also have to take into account that inner function, that 2x squared plus 3. So what we're going to do is we can actually multiply the derivative of that times our original. So the derivative of 2x squared plus 3 is going to just be 4x. And now that product is going to be our final answer. So we are going to be left with having 4x times e to the 2x squared plus 3. This actually brings us to another more general rule for our exponential function. So if we're trying to take the derivative of e to some function u, whenever u is equal, when u is equal to g of x, then we can say that this is actually equal to e to the u, which comes from our initial function, times du over dx. So therefore, we can now use this to apply our exponential rule to whenever we have any power that involves a function. Now let's try another exponential, but this one's going to be a little interesting. This time, we want to find. This time we're wanting to find the derivative of 2 to the x. So this one's a little different than we're used to seeing. Normally, if we have an exponential function, we always have a base of e. But we can actually play with this a little bit and see if we can change it up. What we can do is we can go ahead and actually say that since the properties of e, if we have e to the natural log of any number x, that's just going to be equal to x. So what we can do is we can actually take this function and raise it to e to the natural log. So we can actually transform this and say that we're make it equal to e to the natural log of 2 to the x. Now we can go ahead and play with this. Now we can go ahead and keep playing with this a little bit more. We can actually transform this and say that we have e to the natural log of 2, and then we can go ahead and bring that x down a little bit. Now we're actually in a spot where we could actually go ahead and apply our chain rule, because in this case, our outer function would be e to the x, and our inner function would be the natural log of 2 times x. So now go ahead and look at this. Let's go ahead and apply our chain rule to this. We're going to go ahead and leave our e the same. We can go ahead and leave that function and our exponent the same. And now we just have to multiply times the derivative of our inner function. Since our inner function is natural log of 2x, and natural log of 2 is just a number that's being spit out, we can just say that this is equal to e to the log of 2x times the natural log of 2. And now we can actually go ahead and work back a little bit. Now that we are back, now that we still have, since we still have this e to the natural log of 2x, we can actually bring that back down to our original 2 to the x. We already mentioned that those were equivalent at the very beginning. This actually brings, so now our final answer is going to be 2 to the x times the natural log of 2. And this once again brings us another new rule. We can take the derivative of any constant b to the power of x, and that is going to equal b to the x times the natural log of b. So therefore, yeah, so that way if we have anything in that anything down there, we can go ahead and just translate it. So for example, if it was 8 to the x, we would be left with 8 to the x times natural log of 8. If it was 72, you would just plug in 72 for b. We can use that for any constant that we ever need to. Now let's try something. Now let's take this a little bit further. Now let's have a function to where we can let y be a function of u, and u is going to be a function of g. Or well, u is going to be u will be a function of x. I misspoke. And then x is going to be a function of t. If we plug this in, we are going to be left with getting y equals f of g of h of t. Now, what if we wanted to? Now, if we wanted to take the derivative of this, we're going to have to go ahead and be a little creative. So now let's go ahead. Let's say we want to take the derivative. So we're going to have our dy over dt. As we learned, so earlier we looked into a little bit of our Leibniz form, and this is going to show us why it can be important. So if we had one chain rule, we could say, so normally if we have one chain rule, we can say the derivative of dy over du times du over dx. We can apply the same theory. We can say that we have dy over dx times dx over dt. However, we also know that x is actually that x is a function of something else. We can't necessarily go straight from y to x. We have that little stage in the middle. So we can actually rewrite this as saying that we have dy over du times du over dx times dx over dt. Now this shows how we go from one to another. We go from y to u, from u to x, and u to t, like we did up here. Like we did up here in our original, where we went from y to u to x, and x to t. This shows how we, because of the way this property works, we can use chain rule multiple times. We can, so even if we have more than two functions, essentially we're still going to keep to that outside in rule. We're going to always stay with taking the derivative of the outermost function and then move in, and then just kind of keep moving in and moving in as we take our derivatives. So let's go ahead and do another quick example of this. This time we're going to take the derivative of cosine of 2x to the fourth plus sine of 1 over x. All right, let's go ahead and begin. So let's go ahead and think about what our outer and inner functions are. We can say that we have our outermost function as being our cosine of x, or cosine of u, either way. And we can go ahead and say that our inner is equal to the 2x to the fourth plus sine of 1 over x. Now let's go ahead and plug this straight into our, plug this back in. So if we take the derivative of cosine, it will be negative sine. And then we know that our innermost function is going to be the same. Now we need to take the derivative of our 2x to the fourth plus sine of 1 over x. But if we look closely, we can see that we actually have we actually go in another layer further, because we have this sine of 1 over x. So we actually will have to apply the chain rule again when we take our derivative. So we can actually already know that we can already take our derivative of 2x to the fourth, which will just be ax to the third. But now we have to look at this sine of 1 over x. This is going to be another inner function. Or as a better way to say it, we can treat this sine of 1 over x, sine of 1 over x. We can go ahead and break this down into its own inner and outer functions, to where its outer function is sine, and then its inner function is equal to 1 over x. So now let's go ahead and take the derivative of this. If we take the derivative of our outer function, we are going to be left with getting derivative of sine is going to be cosine. So we're going to have our cosine, and we can go ahead and keep our inner function the same. But now we also have to take that innermost function into account. So if we take the derivative of 1 over x, that's going to be the same as saying that we have x to the negative 1. So we'll be left with getting a negative x to the negative 2. As our derivative for that. So we can actually go ahead and say that our final answer is going to be the negative sine of 2x to the 4th plus sine of 1 over x times 8x cubed minus the cosine of 1 over x over x squared. That's going to be our complete derivative whenever we, this is going to be our complete derivative. For this one, we just kind of slowly moved out and then further and further in. Let's actually go ahead. We have a little bit of time to maybe do another quick one, to where, let's say we have, let's try one more quick one. Let's say that we have we are going to be taking cosine of, we're going to be taking the derivative of the cosine of tangent of x squared. All right, let's go ahead and move forward. So this way, let's try another way this time. And this one's a little easier since we don't have to do any sum rule. Let's actually go ahead and treat this as outermost down to innermost. So we're going to go ahead and have our outermost function being our cosine. We can say that our middle function is going to be tangent, and then our innermost is x squared. So once again, we can rewrite this as saying outermost is going to be cosine. Our middle is going to be tangent. And then our innermost is x squared. So now let's go ahead and apply this. So if we take our derivative of our outermost function, we're going to be left with getting, so we're going to have our derivative, since our outermost function is cosine of u, the derivative is going to be negative sine of our u, which is going to be tangent of x squared. Next, we're going to multiply this times the derivative of our middle function. So if we take the derivative of tangent of x squared, then the outer function of that is going to be tangent. So the derivative of tangent is going to be secant squared. And then our inner function is going to be left alone. And the Now we take the derivative of our innermost function, which is going to be 2x squared, x squared, which will give us 2x. So therefore, we can actually say the final answer is going to be, if we rearrange this a little bit, we can say that we're going to have negative 2x times the sine of tangent of x squared times the secant, or secant squared, of x squared. All right, so that just about concludes it for chain rule for today. So now let's go ahead and start looking into implicit differentiation. When we have implicit differentiation, we need to think about why we would use it. So we actually have two main types of functions. We have explicit functions and then we have implicit functions. In an explicit function, there is going to be a direct relation where we can solve for one variable in terms of another. So what they mean is that we can say that we have y equal, like for example, the biggest one we use is saying y equals a function of x. And, like, we can go ahead and use x to define what our y is going to be. If our x changes, our y changes. And it just spits something back out. It's more explicit because we can just plug something in for x and it's going to very easily spit something back out for y. So like another example of this, there's a lot of examples. We can say that y equals 3x squared plus 2, x equals the natural log of t, and let's say that we have f of x equals e to the x times 2 times 2x cubed, and then our f of x can actually be set equal to some variable. Like I said, regardless of what we plug into that function, we can get a direct number out, and we always just have one value out here. We only have y, and just y is set equal to a function, or x is set equal to some function of t. Implicit functions are a little different. Implicit functions are an implicit relationship between both variables. So what this really means is that essentially we can't break apart the function. We're always going to have both x and y somewhere within that function together. So like some examples are x squared plus y squared equals 25. You have to have, for this, you have both your x and y involved in that function. Another one would be y cubed equals x squared y squared minus 25x. Once again, you can't really like break this apart. You're always going to have your x and y like intermingled with each other. Now, You can sometimes turn an implicit into an explicit function, but you can't always. So, like for example, it would be very easy to solve for y for our first function. To where we could essentially say our y squared equals 25 minus x squared, take the square root, and where we could easily say y equals plus or minus the square root of 25 minus x squared. There is no way we could do anything like that for this. The powers are weird, the y's spread out too much, we can't really break that down. That has to just stay there. But that doesn't mean that we can't still derive it. So overall, here's the way you can derive any implicit function. And I'll go ahead and work through this through an example. So we're going to have a function that's going to be x squared over 4 plus y squared over 9 equals 1. And we're wanting to find what dy over dx is. So what we can do is we can actually go ahead and still derive this. What we can do is, so if they're wanting us to find dy dx, because tx is in the bottom, that means we are deriving our function with respect to x. So we can actually go ahead and just keep deriving as normal. So let's go ahead and derive this function with respect to x. So we get 2x over 4, x squared over 4. If we derive that, we're going to get 2x over 4. Now we have our y squared over 9. This actually doesn't mean that we can't derive this at all because there's no x term. Instead, what we can actually do is we can still derive this term to where we can say that we have 2y over 9. But we have to make sure to multiply it times dy over dx. Because we have to signal that we are deriving with respect to x, we have to make sure to kind of leave that mark that even though we derived y, it is in relation to x. And then on the other side, derivative of 1 is just going to be 0. And since there's no term, we can just assume that that was in terms of x. And now we can actually go ahead and just solve for our dy over dx. We can go ahead and say that we have 2y over 9 dy over dx is equal to negative 2x over 4. You can multiply times 9 over 2y on both sides. And therefore, our dy over dx is going to be equal to negative 9x over 4y. This dy dx, this ultimately comes from using chain rule is how this works, but that proof can be it can be a little confusing. I would recommend asking a prof about the proof for the dy over dx. Just know that if we're doing implicit differentiation, you have to mark the one that you're not deriving. If we're deriving a function in terms of x, you have to make sure you mark dy over dx if you're deriving y. If we're deriving a function of x and y and we're wanting to derive in terms of y, then anytime you derived an x, you would have to write dx over dy. There's actually, you could also derive implicit functions by turning them into explicit functions, but That is sometimes more work, and once again, not all implicit functions can be turned into an explicit function. If we have time at the end of the session, I may go over how you would go about doing that, like similar to what we did with that first example, but that's dependent on time. So now let's actually try another example of our implicit differentiation. This time, we're wanting to find dy over dx of 4x squared y to the 7th minus 2x equals x to the 5th plus 4 to the y cubed. All right, so first thing we can do is that we can go ahead and check to see that we're wanting dy over dx, so we're going to derive with respect to x. So now let's go ahead and start plugging things in. Now let's go ahead and start our deriving process. For this first part, we have a 4x y to the 7th. So in this case, we actually need to go ahead and use our product rule. So what we can do is that we can say that we have so the first thing we can do is let's derive our x. So we can say that we have x squared derived as 2x, so we're going to be left with 8x y to the 7th. And then we're going to derive in terms of y with respect to x. So in this case, we get 7 times 4, which is 28, y to the 6th times x squared dy over dx. And then we can just go ahead and have a minus 2x, so that's just going to be a minus 2, which is going to be equal. And then we have a x to the 5th right here, which is going to simply go down to 5x to the 4th. Lastly, we have a 4y cubed, and that's going to easily be derived down to 12y squared dy over dx. Now let's go ahead and look and see what we have. We have a couple of terms that both have a dy dx in them. And what we can do is we can actually go ahead and try to move those to the same sides of an equation and move everything else to the other side. So what we can do is we can go ahead and say that we have (8x y to the 7th minus 2 minus 5x to the 4th is going to be equal to 12y squared dy dx minus 28 y squared x squared y to the 6th, my sad handwriting, I apologize, x to the 6th x squared dy over dx. Now what we can do is we can actually go ahead and factor out a dy over dx. So where we have 12y squared minus 28 x squared y to the 6th dy over dx. And that's going to be equal, once again, equal to our original 8x y to the 7th minus 2 minus 5x to the 4th. Now we can go ahead and just divide both sides, so we're left with just dy dx equals something. So if we divide both sides by 12y squared minus 28x squared y to the 6th, 12y squared minus 28x squared y to the 6th, you're going to be left with the final answer of dy over dx is equal to 8x y to the 7th minus 5x to the 4th minus 2 over 12y squared minus 28 minus 28x squared y to the 6th. And that is going to be our final answer for dy over dx. It gets kind of lengthy, but ultimately it just, usually it'll come down to just kind of moving things around and factoring out dy over dx. Not always, but especially when we start getting to higher levels of math courses, it's not always going to be this easy, but usually at this level, this is about what we're going to be looking at. Now let's try another example. This time we have 7y squared plus sine of 3x equals 12 minus y to the 4th. And we're wanting to, once again, we're wanting to find dy over dx. All right, so let's go ahead and keep moving forward like we did this time. Once again, we're deriving with respect to x, so let's go ahead and take that into account when we take our derivatives. All right, so if we do the derivative of our 7y squared, that's just a simple power rule, so that's going to give us 14y, and then since we're doing implicit, dy over dx. If we take our derivative of sine of 3x, that's going to be our trig plus chain rule. So our trig is going to give us cosine of 3x. And then our chain rule is going to have us just pull out a 3 from our 3. It's just going to go ahead and have us derive our 3x, which is going to be a 3 that we can just put out in front. Then we're going to have our 12, which is just going to go down to 0. And then we're going to have our negative y to the 4th. We can go ahead and derive this. Once again, it's a simple power rule where we get negative 4y cubed dy over dx. Similar to last time, since we have multiple terms that have dy over dx, we can go ahead and move all of those to one side of the equation and move any terms without it to the other side. So we can actually go ahead and say that we have 14y dy over dx plus 4y cubed dy over dx equals negative 3 cosine of 3x. From here, we can go ahead and pull out our dy over dx, which is going to give us d over dx times 14y plus 4y cubed is equal to our negative 3 cosine of 3x. Just like last time, we can just go ahead and divide by everything that by everything that's not dy over dx. So we can go ahead and divide by 14y plus 4y cubed on both sides. And this will be, now since we are left with just dy over dx on one side of the equation, this will be our final answer for dy over dx. Now let's try one last implicit differentiation problem that has a little bit more, that goes a little bit further. So, even if we have an implicit function, that doesn't mean we can't still have a tangent line. So this time, let's go ahead and try to find we want the tangent line at 0, 3 of the function y squared e to the 2x equals 3y plus x squared. All right, so now first things first is let's go ahead and see how we're going to, so now if we have a tangent line implies that we're going to have a dy over dx. Therefore, we're going to go ahead and find our tangent, and that means we're going to go ahead and derive our function in terms, or with respect to x. So now we can go ahead and say that we have our y squared and our e to the 2x, which are going to be product rule. And then we're going to have our 3y and then our x squared. So if we derive, if we derive that first term, y squared e to the 2x, if we derive that, if we derive that looking at our y, we're going to be left with getting 2y e to the 2x dy over dx. And since we're doing product rule, it's going to be plus, and now we're going to derive in terms of our e to the x. E to the 2x is going to be our chain rule, so we're going to be left with having our y squared just stays the same. E to the 2x, that's going to stay the same. And then the derivative of our 2x, which is our inner function, is just going to be 2, so we can just pull that out in front as a coefficient. If we derive 3y, we're going to be left with getting 3 dy over dx. And that last term is our x squared, which is just another product rule, which will just give us 2x. Now we continue to follow the pattern that we have been, to where we just pull our dy over dx to one side of the equation and everything else to the other. So we're going to have, so let's say we're going to have our 2y e to the 2x dy over dx minus 3 dy over dx equals 2x minus 2y squared e to the 2x. We can go ahead and pull out that dy over dx. So we can go ahead and say that over here we now have dy over dx times 2y e to the 2x minus 3. We can divide both sides by 2y e to the 2x minus 3. and that is going to be our dy over dx. However, we're wanting our tangent line. And if we think back to what we know about our tangent lines, our dy over dx is gonna give us our slope. So first thing, since everything's still in terms of x and y, we need to actually go ahead and plug in our points to see what our actual slope will be at that point. So if we plug in our 0 and our 3, we're going to get, let's plug in our 0 and 3, so we're going to get 2 times 0 minus 2 times 3 squared e to the 2 times 0 over 2 times 3 e to the 2 times 0 minus 3. We're going to, so this leaves us with a 0 minus, we get 2 times 3 squared is going to be 2 times 9, so 18 times e to the 2 times 0, which is e to the 0, which is 1, so this is just an 18. Once again, we are left with getting, we have our 2 times 3 times e to the 0, which is once again going to be but that 3 is not squared, so we get 2 times 3 times 1, which is going to be 6 minus 3, which leaves us with negative 18 over 3, which is negative 6, which is our m. And we can put this back into our point slope, so it's where we have, if we plug this into our point slope, which is going to be y minus y naught equals to m times x minus x naught, we get y minus 3 equals 6 times x minus 0, which will end up leaving us with y equals negative 6x plus 3. So now for the last thing I really want us to touch on today is going to be our inverse trig. Now, our inverse trig functions for the derivatives, the proofs ultimately do come from implicit differentiation, but once again, those proofs can get kind of, they're a little complicated to understand. Like, they're not a lot of steps, it's just the logic behind them can get a little weird. So that's another one where if you want to know more about it, I would recommend asking your prof or just someone who has, an actual degree in math. So yeah, there are a lot of other resources for you to look at, for you to look into proofs. However, we don't really have the time for it today. So let's just go ahead and go over what our inverse trig actually is. So we actually do have, can derive our inverse trig functions. Now, first thing I want to note is that there is a notation thing, so we can either write our inverse trig that can be written as either our trig function, so for this example I'll use sine, that can either be our trig function to the negative 1, or we can say put the word arc in front of it. Those are going to be the same thing. So just in case, so that way if you ever see arc sine pop up, then you know that's going to be the same formula as that sine to the that sine to the negative 1, which implies an inverse. So now let's go ahead and look at our actual equations. So we're going to have, once again, we can use these for all 6. So we've got our sine and cosecant. You can do inverse cosine and inverse cosecant. I mean, secant. I think I misspoke right there. And then we can also do this with our tangent or our inverse tangent. Give me just 1 second so my laptop does not die on me. There we go. So yeah, as I was saying, we can also do this with our inverse tangent. And our inverse cotangent. So now let's go ahead and go down the line. For our inverse sine, we're going to end up getting the formula 1 over the square root of 1 minus x squared. For our inverse cosine, it's actually going to be the same thing, but we're going to have a negative out in front of it. And then our tangent is going to look similar, but just a little different. So where we get 1 over 1 plus x squared. Now let's move on to the other ones. So this time we're going to get, for our inverse cosecant, we're going to get negative 1 over the absolute value of x times x squared minus 1. So it's mostly similar to our inverse sine, just a little bit different because of that negative and that absolute value. Now if we look at our secant, this is going to be very similar to the relationship between sine and cosine, where we get the same thing, but the opposite sign. And then cotangent and tangent are going to be the same, but with an opposite sign. So these are going to be the 6. So we have formulas for all 6 of inverse trigs. So now let's go ahead and do a couple of examples of these. The first one I want to do is I'm going to find the derivative of square root of x times the inverse sine of x. So for this, we actually can go ahead and split this up into two functions to go ahead and use our product rule. So if we go ahead and apply our product rule, if we go ahead and derive that square root of x, that's going to get us x. Since the power is initially to the 1/2, it's going to be the negative 1/2, and that 1/2 is out in front, times our inverse sine of x. If we go ahead and now if we derive our inverse sine of x, this is just our plain function. We can just plug it in to where we get one over the square root of 1 minus x squared times our square root of x, which we can actually just go ahead and just plop that on top. And this is going to be our final answer. All right, now let's do another example. This time, we're going to we want to find the derivative with respect to t of arctangent of 3t minus 1. So this one's a little different. So of course we do not have an x on the inside, but we can actually still go ahead and solve this using our chain rule. With 3t minus 1 being our inner, and then arctangent being our outer. Alright, so if we take the derivative of arctangent, so the derivative of arctangent of x is 1 over 1 plus x squared. So we can go ahead and start plugging this in. So we get 1 over 1. But since we have a 3t minus 1 instead of an x, we're going to go ahead and leave that 3t minus 1 in the parentheses and square that. Now we take the derivative of our inner, and the derivative of 3t minus 1 is just going to be 3. Therefore, our final answer is just going to be 3 over 1 plus 3t minus 1 squared. All right. We did not have enough time to get back to trying the explicit form of turning something into an explicit form. But once again, if you want to go ahead and try that one at home, for that one, what you can, once again, that function was going to be x squared over 4 plus y squared over 9 equals 1. And the final answer you get should be dy over dx should be negative 9x over 4y. So if you want to go ahead and play around with trying to go ahead and turn this into an explicit function and see if you get the same, please feel free to do that. Good luck on any future upcoming assignments, and I hope you guys have a wonderful day.